Question, sir.
Hello. Testing. Is okay? I don't think it's working. I know everybody, but I didn't meet you. Huh? My name is Datta. Huh? Okay. Hello, sir. I didn't meet you also. Okay. Chemical engineering?
No, petroleum.
Petroleum, okay. Others I have met.
Good afternoon, friends. So welcome to this expert talk by Professor Joydeep Datta.
It's not working.
So let me introduce Professor Joydeep Datta. He is currently visiting research professor at IIPE, and he is a distinguished materials scientist at KTH Royal Institute of Technology, specializing in nanomaterials for energy and environmental applications. He has over 35 years of global academic experience, authoring 3 textbooks, publishing 300 plus papers with an citations of 24,000 plus and H-index of 77, and holds 15 plus patents. He is an award-winning author, which is Choice Award for Outstanding Academic Title of 2010 from American Library Association for the textbook Introduction to Nanotechnology. His research focuses on application of functional materials in water purification, green hydrogen, and sustainable nanotechnology. His research was selected in the top 100 list by the Swedish Academy of Engineering consistently in 2020, 2023, and also 2024. A pioneer in decoupled water electrolysis, he ranks among KTH's top 25 researchers. As a founder of 4 deep tech startups, he combines academic excellence with leadership experience, having previously served as vice president at AIT Bangkok and in senior positions in companies. With this brief introduction, I invite Professor Joydeep Datta to deliver his expert talk for the next maybe 30-40 minutes.
Thank you.
Yeah, thank you.
I'll
Sir.
make it short.
Yeah.
Is it working? Okay. So, good afternoon, and I will give a slight twist to this talk because you guys are just moving in to a new place. My whole career has been a life of a gypsy. So this is my career that I had. I started off my PhD in Kolkata. Thereafter, I went all the way to Japan, somewhere here, down here. Then from Japan, I had gone to Europe, Switzerland, where I spent a decade. Then, okay, this one was a stop in France. Even I am forgetting, it's such an old time back. Then I stayed in Switzerland for 10 years before I decided to come back closer to my hometown. And that's how I came to Bangkok. Okay? So in Bangkok, I spent another roughly 10 years. But then I was being pushed more and more to administration. I was the vice president. They were pushing me to become the president of the university. So I decided to quit. Okay? On my way back to Europe, I spent about 4 years in Oman. So every place, I went, I restarted. So it's a good chance for you, now that you're going to move to a new campus, or you have already moved, move your labs and you will see that you gain out of it. This is my, more or less, the career. I spent some time at EPFL, AIT, Sultan Qaboos University, and KTH. But I'm a mix of academia and industry. I spent some time in industries. As you can see, in this short period, I changed a lot of industries. That means I didn't enjoy that much. Okay? So after that, I moved, and currently I am at KTH. KTH is Europe's top engineering college within the first 2, 3. Actually, I think we are second, ranked second in Europe. Worldwide, in the QS ranking, we are top 100. Times ranking in engineering, we are top 50, and so on and so forth. KTH has about 200 or 368 professors. We are about 21 chair professors. I'm lucky to be one of them. And then we have 250 associate professors, and we have another 1,500 academic, which means assistant professors and lecturers. Okay? So it's fairly a big size institute, catering to about 15,000 full-time equivalent students, out of which 2,000 are slightly less. I think now we have 1,800 PhD scholars. So it's a research-intensive university and cutthroat, like anywhere else. I will dwell you down now to my past a bit. As a youngster, mostly you guys' age or even younger than you all, I arrived at AIT. I had a small office, 2 meters by 1 meter. And I went to the dean and asked, where is my research lab? Dean said, Richards, you can do it in the students' lab. That was the beginning of my shock, coming down from EPFL, which is a state-of-the-art university with very high research potential. First thoughts always to mankind is that, no, I should go back to Switzerland, I should stay there. Second thought, I have never looked back. So I said, now I'm here, fantastic, let's build up something. In front of my office, there was a corridor. I emptied my office, put my desk outside in the corridor. So that became my office. And this small 1 by 2 meter room, or maybe slightly bigger, it's a really tiny room, maybe 1/6 of this, I turn it into a lab. Okay? Of course, things happen, and then from there, within 3 years, I established the Center of Nanotechnology. In the history of AIT, till the point I established this, nobody had brought in that much amount of money, even the local Thai people, to establish a totally new branch in AIT. So I did that. Then, when I moved to Oman, it was easy. It's like you guys. The government gave money. In AIT, I had to raise every single penny myself. But in Oman, I had an endowment. It was $10 million. So it was easy life. Okay? But in order to construct something out of that place is a nightmare. You think India is bureaucratic? Go to Middle East. It's a super bureaucratic environment. But anyway, I established my lab within first 1 year by negotiating with chemical engineering to donate me some space in their building. It took me 6 to 7 months to do that. And then it was high-speed construction. I'll show you from what stage I put it up. I put in my first equipment in 2012, and thereafter it continued. The expectations of the university was that I produce 1 paper a year out here and so on and so forth. So end of 5 years, I was supposed to produce 10 papers. Okay? I gave them more than 50. My target here was to produce 1 or 2 PhD students because they knew that establishing the lab would take me half my time. They didn't know that I had the same genes as Shalivan. You have to work hard and get things done. Okay? So ultimately, we graduated about 4 PhD students, several master students. I just put in 5, which I graduated, but I brought in other faculties who became part of my center. So we were a very exciting hub of people. In AIT, when I left, I had about 50 people group. In Oman, when I left, I had about 25 people group. Okay? This was the grand opening. So you can see that I'm not lying. I was in Oman. Okay? The center in Oman, this is how I started. Or this is how I finished. Okay? You can see that. And this is how the lab was. It really was nothing much. I used glass everywhere, and it came out very, very pretty. But I started out from here, giving out the contracts, giving out the tender, and I had to do everything myself because I was reporting directly to the minister. It was a national chair in nanotechnology. A minister doesn't have time to give a contract for a few $100,000. So I had to do all the paperwork in Arabic without knowing anything. Then get hold of workers, mainly from Pakistan, India, and Bangladesh. I used to sleep in this place to try and finish the lab. Okay? That's how I started. Then it looked, even before it happened, it started looking like this. Then when it was finished, it looked like this. And when it was finally done, it looked like this. Okay? And this is when I finally said goodbye to everyone. Huh? So the message there, and by the way, this guy was my oldest PhD student. He even passed away, unfortunately, but he would have been about 69 now. So there were few things that were spread as rumors about me. When I arrived there, it was quite interesting. I was going to meet the president, to the minister, and the research council chairman, he was taking me there. The minister was looking around. So then the chairman of research council is an old Omani gentleman. He stayed a lot in Cambridge. He smiled back to me. He said, Professor Datta, don't worry. She is looking for, it was a lady who was the minister, she is looking for gray hair or no hair person. That's why, hey, Srinivas, okay, thank you. That's why, you know, basically you are not being entertained. So then I was introduced to her. Of course, at that time, I was much younger. It's nearly 20 years back. Okay? That's how I started. And my good friend Srinivas, I had met him in EPFL 35 years back. And thank you very much for coming all the way from Wimley.
I keep hunting for you here.
Thank you, sir. Huh?
Nice to see you.
At KTH, my research is focused on these aspects, not at all times, but these are, you can say, the core areas that I delve in. CDI was something that was motivated by my mother in 2004 because I had come to India to visit her and her RO system was not working. So she asked a scientist's son, can you fix my RO system? And I am from physics, electronics background, same as Srinivas. I knew nothing about membranes. Went back to Thailand and I was thinking, how they clean water. Then I realized that they were cleaning water today by taking water out of the salt. If you think about all the membrane processes, you are taking water out of the salt. And I was thinking, it would be nicer if we can pluck out salt out of the water. And that gave birth to these capacitive deionization systems. I thought I had come up with the idea, but then I found out a scientist called Patel, who had already thought about it when I was born in 1964. Okay? So of course, you know, it was nice to see that I'm not that thing. Solar photocatalysis and green hydrogen production, these are a couple of things that I'm working quite a lot. And of course, these are part of this one. Advanced food packaging materials, we are doing some work there, wherein we are primarily working with biopolymers to try and increase the shelf life of fruits and vegetables. So I'm collaborating heavily with one of my old postdocs who actually has returned to India. And I have an associate professor who is handling that. Okay? In a nutshell, I do fundamental material sciences, and I emphasize on this word fundamental because that is how I interpret all the data. By applying them, addressing urgent global challenges. Water, the CDI, food coating, and in energy, we have stopped working on solar cells. I am entirely focusing on green hydrogen production. At least there, it was my original idea which I'll present you. Till now, I haven't found because we submitted the patent, it was granted, so that means it was my idea. Okay? One key point to our work is I only do research out of the box. The regular stuff, I leave it for the others to do it because I'm not so good. I'm not a good follower. So this is what we do because one thing is clear. Like Deming had said, it's not necessary to change. You can continue to do what others are doing if you don't want to survive. That's fine. Okay? Plastic, we talk about a lot. Food waste, we talk about a lot. Plastic pollution comes in. Why? Because polyethylene up to polypropylene takes between 200 to 500 years to degrade. You don't have to be blind or you don't have to be intelligent. If you come to India, you can see plastic pollution everywhere. Surprises me, but that's what it is. Why plastic is so important for us? Because it helps reduce food spoilage. Okay? But we definitely need to find some way out. Water pollution, nothing much to talk about. During just this visit, I have read about so many people getting killed in Indore. It's a burning problem right at the doorstep. My friend Srinivas, he has his well water contaminated with E. coli. So it's there everywhere, and that too in a posh place like Wimley. So if it can happen there, it can happen anywhere else. So what we thought about is, can I make something, out of waste? Take the waste from shrimps, convert into a biopolymer, and then use it for food packaging. That's one of the first things we did. Of course, in order to do that, you can do it with, a lot of steps are there. I will not be going too much in detail. Anybody is interested can ask, because then I will not finish the talk in due course of time. So what we are basically doing is we are deacylating the chitin. Make chitosan, it has a lot of amine groups, and then you can also make changes onto the chitosan and increase the performances. So like I graduated a PhD student who was supposed to make green chitosan for green. Why? Because we wanted to take it from food waste. And you have two types of people. Some people who eat meat, like us. And there are also some people who don't eat meat, vegetarians. So for the vegetarians, we extract from waste fungi. The champignon or mushroom. Okay? So we have done a lot of different types of coating. One of them is anti-fouling coatings for boats. The other one is anti-fouling coatings for food packaging. But these are fine in terms of science. Anybody interested, you can take a look at my papers. You'll find them. But more interestingly, you can see it to believe it. Okay? These are avocados. And you can see that up to 11 days, we were able to keep the avocados once they were coated. And it's more clearer from these cut fruit. So we have done assays on apples, oranges, pineapples, bananas. In all cases, we have achieved an enhancement of 7 to 8 days. And remember, all these cases, we are not using any fridge. And most of these cases, you will say that Sweden is a fridge by itself. No. Most of these assays were done during summer. So it was quite okay. So another interesting thing here, of course, all of them are published, so you can take a look there. We were trying to mimic the shark skin. Shark skin has a very rough surface. If one can have such a rough rugosity, then in that case, that would be anti-fouling. So that's what we read. So I took some chitosan and tried to use them, modify them, and put them there. But it so turns out roughness doesn't have too much to play. It's the surface properties and the good or bad mood of the bacteria or the biomass that determines how you would foul. So it's very difficult to actually prevent anti-fouling in ships. Very difficult. We haven't found any solution yet. Last week, we talked about this, wastewater treatment. Okay? And now, I will just talk about the AOP a little bit more in details. If you look at why everybody is talking about AOPs, it just comes from here. These are oxidizing reactions. And you have very high activation energy, right? So when we are talking about hydroxyl radical, which I often talk about, is about 2.8. 2.8 eV, you can oxidize a lot of things. A lot of things. Okay? So, based on this, you design, Fenton processes wherein you are actually having the iron chloride in the solution. But we don't do it that way. So what we do is we are immobilizing iron on activated carbon cloth. And as you can see, that you get a removal percentages of both color as well as COD. So that means you are able to degrade. Okay? That's typically what you do to publish a paper. AOP is becoming very important now because we have pollutants in water which can't be taken otherwise. And that is actually seen out here. If you look at it, it's just exploding the number of papers in AOPs. I might have missed some. I just quickly did some search yesterday night to show it. This is why I'm talking about AOP so much, because that's the only way out to handle the recalcitrant, pollutants, as well as like things like PFAS, antibiotic resistance, or even pharmaceutical byproducts, or even simple petroleum byproducts. But then I'm never happy. I want to be sustainable all the way through. So what we did was we took some of these windmills, which were decommissioned, extracted some substrate from there, which is nothing but silica fibers, and then we plugged in structures like this to test the Fenton reactions possible. Okay, so it was something like this, and essentially this is how it looks. You have them coated on top of these glass fibers, and this is basically zinc oxide with a cover of tin, because otherwise zinc oxide will melt at pH 3-4. What? What GM? Graphene. I'm testing. He was sleeping. That's why he didn't see earlier. Okay? I saw him sleeping. That's why he didn't see earlier. So, these are some of the, decolorization strength. You can see photofenton reaction. We are able to do about 85% reduction. Same here. Decolorization. Oh, these are two conditions. One is pH 3 and pH 6. Because all of these, I want to do it at pH 6. And that was also pushed through here. So you see, at pH 6, we are able to do that. Because Fenton reactions per se is only valid at pH 3-4. So we have been able to push it to pH 6. But I'm never happy. As a scientist, we can never be happy. So now what I'm trying to do is trying to see if we can use Prussian blue analogs to have the iron 2+, 3+ transition right in the crystal itself. Okay? So we did some preliminary work, and this is how it looks. So it's looking promising. The iron leaching is very limited. So the whole vision that I had over the past 10 years, now it seems to be upcoming. And now I think others can take over and do better job than me. I have to find some new greener pastures. Okay? Just to try and tell you, I always do some science with a long-term vision for application. This is what we have achieved. Before, about 6 years back, I had put up, no, COVID was when? Yeah, 6 years. So during COVID time, we had put up a plant wherein we were reducing the PVCs to about 94% of its volume. And this took between 2 to 3 weeks. I wasn't happy, so we improved on the process. But anyway, the other thing is, if somebody is working with plastics, please, if you want to look at degradation of plastic, you can use our software, wherein you can basically measure the SH and NH bands straight away. This software is called Emma. One of the girls was Emma, another was called Michelle. So that's why we call it Emma. So this is available free for everyone, no problem. And it's a fairly simple way of characterizing. This is the newest results. I can tell you we got it just because yesterday I was unable to show, so I got it just fresh over the night. So you can see that we are able to actually degrade 80% of the polypropylene particles, which is actually one of the hardest to degrade, within 50 hours.
What is the end product?
End product, we don't know. You can study. It's well known in the literature. So, because if you do Fenton reaction or degradation by anything else, end product will be the same. You're cleaving from bigger molecules to smaller ones. Okay? But this is installation that I did in Slovenia, and this is how the thing was. It's a fully automated system that is working there. Now we have stopped because it's snowing. Since water goes through the tubes, it would freeze. We don't want it to break. Okay? All right. So now I come to my mother's inspiration. I briefly introduced it yesterday. A supercapacitor with 2 nanostructured electrodes. 2 reasons. One, it has to have reasonable conductivity because it's electrical electrode. Second, it has to have a huge surface area. So we are using activated carbon cloth, which has a surface area of about 1,200 square meter per gram. You can even have something like 2,400, but from my viewpoint, I see that 600, 700 is good enough because anyway, you'll not be able to enter all the macropores. So once you apply a small voltage, then you move the cations to the cathode and anions to the anode. And once you are done, so you can wash it away. Okay? So we first filed our patent in 2005. And since then we have filed up about 20 different patents on this class. Okay? So I have more than 35 patents now, Seshadri. Okay? I don't claim. But then, as usual, we are never happy. I want to now make use of charge transfer in a crystal to increase the capacitance. A capacitor, a general capacitor, when you have an electrolytic capacitor as we call, the way it stores charges is through the double layer, the Guy-Chapman layer. And the double layer is formed because if I have negatively charged cathode, I have sodium coming in, then you're forming this sodium and the chlorine double layer. So this sodium will actually not allow new sodium to come. Okay? So even in a capacitor, you will see that it charges very fast and then it actually saturates. It's an exponential charging. So overall, in a supercap or an electrolytic capacitor, you will only charge up to 80% of its total specs. Otherwise, it will charge, but slowly. In our case, what we have noticed is that since we have a dilute electrolyte, if we charge up to about 46%, then beyond that, energetically, it is not very favorable. We have calculated that thermodynamically and looked at it also in experiments. So roughly we say, okay, fill in the tank up to 40%. Half tank is better than full tank because I can have 2 or 3 half tanks for the same energy cost. Okay? So we are able to do, 1 cubic meter of water treatment within 1 kilowatt, which is by far some of the best results that you can think of. And also our water wastage is less than 20%. I checked on also the stability of the electrodes because we are using carbon electrodes. A small voltage you are applying, you will have some oxidation of the carbon. Okay? But it seems that we can more or less see that, generally these electrodes could last in lab conditions at least 1.5 years. But then the company has found some electrodes, they degrade around 6 to 7 months. Some others are running for 5 years. So I still don't know why, but we'll figure out soon. Okay? I think it is because of what type of ions are coming in and what redox reactions occur on the surface. In order to come up with this story, it took me 20 years. Started with my mom's thought. 2006 made the first capacitor. And actually, this was a failure. My salt adsorption capacity, it had an efficiency of 0.03%. Normally, others would have given up. But I was convinced that I was doing something wrong. And what I was doing wrong was I had used aluminum kitchen foil as the electrode, and aluminum oxidizes very easily. So you are actually putting a barrier layer for the capacitor. But then thereof, we kept doing. This is the first one where we actually came up with the invention of completely through. In our case, we are not making plates wherein water passes on the surface. In our case, water goes from top to bottom because we are using porous cloth. It's like a cloth. So it's probably the birth of the first flow-through capacitive deionization. Now many people are doing it. Earlier, the same people used to laugh at me, which is standard. Why am I using completely off-the-shelf electrodes? Should be better if I had done some treatment. Ujjwal, your thought? Everything has to be treated. You will not take something simple. Chemist thought. So, but then it so turns out that many people have started using that. So it was established. In the company, what they are doing now, the company, by the way, I think we launched in 2007, 8? I don't know. No. 2017, 18. So it's less than 10 years old. Okay? So the company is changed a lot. This one has 18 of these type of cells. The small one that you saw is about, small one is Eppendorf that I converted, okay? So this one actually is 6 of the Eppendorf together. So it's big, about this big. So essentially this has 18 of them and so on and so forth. Now the standard one is there are 48 such cells in the module. And these have been put in about in a container wherein they can go up to 15,000 liters per hour. Okay, so it's now gone in for industrial applications. Okay. The good thing about CDI, like I showed yesterday, it's a close to one solution gives you all. So you can take out multiple contaminants using CDI, which is not the case with competing technologies. But many of these has to be established now in the industry. I hope that in the near future it'll be done. I gave a quick example of API removal yesterday using CDI. API is the drugs. And then I gave also my observations that we are able to take away, using a small system of the company would be able to take away about 3 cubic meter per day. So in the bigger one, we should be able to do much more. I haven't calculated. Okay. We have done some work on PFAS removal. Because look, PFAS is removed by adsorption on carbon. Our electrodes are all carbon, except that we are giving it an added boost by putting in a voltage across. But I don't believe that PFAS removal will be solved like this, so I will not pass into that. And today we are thinking about what can we do next. Because the company is doing the regular water treatment. I don't want to get caught there. I want to now use the similar architecture to try and do something else, wherein we are basically trying to collect the nitrates from the runoffs or from the wastewater treatment plant or from nuclear plants and convert them into ammonia. So preliminary results have started coming in, and we see that we are able to be competitive in terms of ammonia production. In terms of ammonia production, we are quite competitive to Haber-Bosch process. And you were asking me how we do it. We just use the indophenol. Okay? Or I think you were asking, either of you were asking, and you were telling me. Yeah. So it's
that as UVs also can get.
yeah, this is the easiest. You don't have to go anything D2 or anything.
I was thinking that people are using that NMR.
Because they have NMR in the lab. Look, in microplastics degradation, okay, thermogravimetric analysis has become a standard now in papers. I was the first one to use it. Why? Because we have one in the lab. So my thought process was, if I have a ball of plastic and then I degrade it, I'm not going to degrade it uniformly from the surface. I'm going to make pores and holes in there. So TGA, I should be getting a shift. DSC I will not, because the crystal structure doesn't change much. And yes, I saw some changes, so I said, okay, it is this many % degraded. Then we wrote this FTIR, program to try and also check the degradation. It's just a ratio between the SNH or NNH. And then I compared that result with the TGA. I said, there's a correlation, published a paper. And now it's become a standard. The reason I did TGA in the first instance is just because we have it.
Professor, so do you have the cell design set up here? How you carried out this total experiment? You have this here?
No, I can't because I have a patent ongoing. I don't have any membrane. It is a no.
So not in each cell.
No, it's a real device. We are making about 200 milliliter of ammonia. It's small, huh? 200 milliliter of ammonia per hour.
That is also good and also.
So our first prototype will be put in by June this year in a fish farmer's place in Denmark.
Nitrates are available.
All fish farms have that because you have a lot of nitrates there. Okay? So we'll be concentrating nitrates using CDI and then pushing that nitrate to make the transformation.
So this is now under disclosure of E.
Yes, I can't tell you more than that. Okay? But it is based on my concepts of capacitive deionization. A third thing from CDI, because you know, Professor Srinivas and me, we have similar background. We are applied physics guys. We only understand electrons and holes, a resistor, capacitor, or inductor. Anything I forgot, Srinivas? That's what we know. So all the design that I think of comes from there. So I was always wondering that hydrogen is being made in a lot of ways. Faraday made the electrolysis of water long back. It's not new. When I was in school, I did electrolysis of water using 2 pencils. All of us did that. So why it doesn't work so easily? So it's essentially when you see that you are actually talking about hydrogen and oxygen that are produced at the same time from water. So first thing which everybody talks about, making oxygen is a 4-electron process, making hydrogen is a 2-electron process. So I need lower energy for making hydrogen than making oxygen. So the thought process came in my mind, if that is the case, then I should selectively be able to make hydrogen and selectively be able to make oxygen. Because, you know, when there are 2 electrons involved and 4 electrons involved, the work function is different. That kick-started my thought process. It's a 7-8-year-old story. 2 PhD students whom I had assigned this, they quit. One of them even complained to KTH that I was going crazy. Okay? Then during the COVID time, when everybody were working out in solitude, you know, if you had small group of people, they became the best friends in the world. I had 2 master students from Spain who were visiting my lab. Marie Curie, you know. And one of them was a very sweet little girl. She was even taller than me, but of course to us all a little girl. She was not very smart, but she had a very broad mind and open mind. So I told her, look, you have no choice. You're here for three months. Nobody else is coming to the lab. Let us try to work on this. So between her and the other Spanish student, we started working on it. I had a PhD student those days working on CDI for his PhD. He was from Chile, or he is from Chile. So that guy, since it is common language, he was talking to these kids. He saw results are coming out and he had refused to do it before. And the guy is extremely smart. So once he saw some results coming out, he started discussing with me And that was the birth of it. So finally, the idea of making hydrogen separately from oxygen is not that stupid. So I'm going to present to you, ladies and gentlemen, an electrolyzer that has no membranes separating it. The way I work is that when I'm doing HER, I will stop doing HER at a point where there can be emission of oxygen evolution. So oxygen evolution normally happens at an overpotential of 1.8, 2 volts. So what I would do is when I'm scanning the voltage, I will go from 0 to 1.6 volt, minus and plus both sides. Okay? And then I can reverse the potential and bump up the power to get the OER done. So in other words, we are talking simply about charging during the hydrogen production and discharging during the oxygen production. Back to the same capacitor idea. So this was the birth of what we call the supercapacitive electrolyzer. And it works like this. So you can see that when I'm producing hydrogen, I am storing the energy, storing my oxygen in the other electrode. My other electrode, I have a lot of experience with making electrodes with carbon because I have all these 25 years of experience making capacitive deionization. So I have a capacitive electrode that we make where we store all the oxygen during the time hydrogen comes up. Once this is saturated, I stop it. Saturation, how do you see? If your capacitor starts storing, charges, then the voltage across goes up. Srinivas used to teach that in Delhi University. You can cut off the voltage at whatever point you want. And once I do it, I'll just switch the power. So remember, this carbon, if I put in a voltage of 1.6 volt or higher, it would oxidize. I don't want that. So I would save my carbon, but also I can use the other electrode. There are two catches. One, the catalyst that we use has to be good for hydrogen evolution as well as oxygen evolution. It shouldn't be the best for either of them. But the total water oxidation, it should be good enough. Second, I will only produce hydrogen half the cycle. The other half is idle. Okay? That means if in a standard hydrogen electrolyzer, you have 2 electrodes, one is producing hydrogen and another oxygen, and you have membrane, you'd continuously get hydrogen. In our case, you'll get hydrogen once and then oxygen next time. No worries, you put in 2 of them together and they can switch. Okay? Big advantage that we have is whenever we produce hydrogen, we produce the purest form of hydrogen. There is no mixing of oxygen because there is no possibility of interdiffusion. Second big thing is that hydrogen-oxygen mixture is more explosive than my wife. So, we are foolproof. It can never mix. The third important thing is the membranes are about 1/3 the cost of an electrolyzer. Not only the cost, membranes are the cost reason for failures of electrolyzer, and also having membrane, and since you have hydrogen and oxygen produced at different voltages, if you have any fluctuating power, then you have to shut down the electrolyzer. Like you will see in alkaline electrolyzer, you have to shut down the electrolyzer if your power fluctuates less than 40% of its peak. Our case, we don't care. It's a capacitor, it charges, discharges in its own way. Yes, it is slower because it produces less hydrogen, but we don't care, you don't have to shut it off. So that is what we say is the supercapacitive electrolyzer. And till now, it looks to be quite reasonable. Degradation of the electrodes will be there. All electrolyzers will have. We also have the same. But we are getting better every day. So what has translated to is now, we possibly have the world's first supercapacitive working electrolyzer, because we have about 1 kilowatt electrolyzer that is running continuously, and we are now preparing a 25 kilowatt that we will install in No, Rajasthan is 64 metric ton day production. No. This 25 kilowatt we'll be putting in Sweden for testing. So this product has been already tested at customer site, but with the 1 kilowatt one and the 5 kilowatt one. But we are not even talking about 5 kilowatt one, because we go from 1 to 25. Now we have no issues of confidence. Okay? Dynamic response has been tested. Looks like it is good. But it's continuously going on, and these things, I can't do it, so I'm collaborating with our friends in Luleå. They are very good at that in optimization lab. But what we have already proven is that we can provide hydrogen at less than $2 per kilogram. Possibly, because my target when I got into it, I used to say that we'll make European quality electrolyzers at the cost of a Chinese electrolyzer. And that's where we are heading to. Okay? But as scientists, we are never happy. So currently I have a working electrode that the company is using, but I'm already working on how to improve it. Okay? You might have noticed that I don't work in 1,000 different materials. Chemists normally like to cook all the time. I focus on something and then, push from there. Like zinc oxide nanorods. The first paper I published was in 2004. I'm still using the zinc oxide nanorods. The issue is, I'm not that smart, so something I have learned, why to leave it, but if I just continued like I was doing before, that would be useless, so I'm trying to use them for different other things. Okay? For example, one of the applications we had was zinc oxide nanorods on optical fibers for directing signals and making the sensors useful. This is a quick comparison of the EU hydrogen joint undertaking, and I have compared, various type of technologies, how much degradation happens. In our case, probably the degradation is a little bit more than 3 microvolt, but we will be there. It's coming. Okay? And so, I hope I have given you some insights. KTH is my third place where I built the lab. This is how the lab stands today. Okay? So, again, I remind you, you have a tremendous opportunity now to build up your space and to really get going and put IIP on the map. I would be doing injustice if I claim that I have done all the work, because I have done nothing except troubling the students 5 times a day. Okay? And that will be conveyed to you all by your own student Komal. They are always at the edge. Okay? Thank you very much for your patience and welcoming me to IIPE. It has been wonderful past 25, 30 days that I've been here. And today I will be going back. First to Kolkata, and then Sunday I'll fly back. Okay? Thank you so much. Yes. Before Ujjwal, ask. No, before Ujjwal. Ujjwal will have questions. Yes. Yeah.
Sir, this nitrate to ammonia reduction, in our case we use HCl and in between nothing and membrane. What I observed that electrode gets degraded or something because when we test the chronoamperometry or chronopotentiometry, after 6 or 7 hours the voltage is increasing. But in your case I have been 18 hours. Did you change the electrolyte in between or it is continuous?
No, ours is a continuous mode.
Oh, the electrolyte is continuous?
Yes. Continuous mode. No, that is not the major thing. Actually,
Yeah, it's quite stable.
it is stable. Otherwise, I wouldn't show it. This is patented.
So it's continuous flow mode.
Yeah, it's a device, man.
It's a device.
But one thing please keep in mind, that what you get in HCl, expect half of that when you make a device. It doesn't correlate. And also what you optimize for HCl, I had a Indian postdoc. He optimized everything for HCl, spent over 1.5 years. I was telling him, please don't, start applying. But he was fundamental chemist, you see. And then end of the day, I had to just trash all the data, waste of time, and just pick up on some others to make it for the cell. It doesn't go, at all. All the trends that you see from HCl doesn't work. I can give you a whole table where we have compared all of them, and I see that it doesn't work. Okay? Okay. Any other question? Let me see if I have it here, I can show you. Huh?
The membrane-less electrolyzer, how much is the energy efficiency maximum you observe?
Okay. What is the energy efficiency of a standard electrolyzer?
So maximum up to 60% I have seen in papers.
In a module or cell?
No, in a module.
What size of a module?
Like lab scale, type something like in a stand.
No. Faraday efficiency you can get
Faraday elements we can get.
Yeah.
But they are because of the overpotential.
for HHE or
Sir, I'm taking about
Or alkaline, generally 65 to 70%.
70%. Yeah, this is also, it's actually for the size you say, it's 77%. But I don't talk about it because I don't believe in these results until you have done at least a liter a minute. Like 1 kilowatt is what? 1 liter a minute. So at any time, my lab has a liter a minute of hydrogen. Okay, because Raka, the problem comes in, chemists, they are there for multiplying the papers. And they publish so much crap these days that once you start designing the devices, it's a different ballgame. We have a problem here. Chemical engineers simulate what could be the issues. Chemists, they think that they can always make a better cuisine, always, by changing a molarity, changing temperature, changing speed of rotation or whatever. Physicists, they study one device but thoroughly. Srinivas, am I wrong? Okay? So, me being neither a chemist nor a physicist, not a chemical engineer, I'm a bad mix of all of them. Yeah. No, my basic core discipline is physics. So we work on the device quite a lot. And that ultimately makes, I know that you guys will have to publish paper, but take it with a pinch of salt. I'm trying to see if I can show you the table. I don't know if I have it. I didn't want to frighten the vegetarians with our work on coating. That's why I took it away. You see, this was on pork meat we did to try and directly put biopolymers on pork meat.
So here also I had one.
Yes.
So when you coat the fruits or meats with chitosan membrane or any polymer,
Not membrane, we spray it.
spray it.
Yes,
So
or dip it.
Does it get dissolved when it is in contact with water? Because chitosan usually in acidic medium get dissolved.
How much acidic water do you drink? Here you get acidic water in your tap water?
No, but sir, but water also it get dissolved, but not that fast.
Okay, I will give you acetic acid, vinegar, and I'll give you water, and I'll give you chitosan. How long do you think it takes to dissolve?
Acetic acid, it will dissolve within 4 to 5 hours.
No way. You do it, you get a Nobel Prize. It takes minimum 1 full day. So, that's the issue you guys will have to come out with. For a practical application, nobody is going to put an apple in acid water. Okay, even if it was 4 to 5 hours, you shouldn't even, thought process should not even come that it would be unstable. You understand? Actually, chitosan is very good for coating. Why? Because it absorbs water up to 50% of its volume. So you can keep your fruits moist and look better. Actually, I don't have the picture, but we had done a study on organic lemon. In the West, you had the organic lemon, which was double the price of normal lemon. So we did work on that, in which we coated some lemon, this much, and we did not coat some lemon, and we put it in ICA. It was the ICA store we are working. It's a supermarket there. And we put in a sign, please don't take these lemons because these are being tested by KTH. You have to give that. Our basket was nearly empty, whereas the lemons were looking much nicer than the other one. Because organic lemons, they get spoiled within a few days. Okay? So you have to valorize like this. You understand? Don't think always the negative. Think always the positive and then turn it around. You should learn from your director. Worst situation, he always thinks, oh, no, everything is fine. Huh? Science also is about confidence. But I must admit, when I found out that there are no papers nor patents on this supercapacitive electrolyzer, I was so jittery that I asked RISE, the Research Institute of Sweden, to come and do an independent evaluation. So I told them what I was doing, and I was getting hydrogen, went out of the lab. They spent 1 full day, had to pay 50,000 kroner from my own pocket. But I did not want to come up with, which is about 5 lakh rupees, because KTH will not pay. But I paid that because I wanted the result, to say that at least I don't have a Pons and Fleischmann. You remember Pons Fleischmann? Okay. Good. Any other questions? Now, Ujjwal, without a question, I'm not letting you go.
So this Chitosan you get from market or you derived from some raw?
We have very good friends like you. We collect, no, we get these mussel shells, you know, blue mussels, the crabs, from a crab meat manufacturing company in Greece, and we make it ourselves. Because ours is a green process. I didn't come to it because it's also patent protected.
Because how pure and how green that Chitosan, that is one question.
What do you mean by how green or
The preparation, source of the raw materials and preparing the Chitosan.
you look at my, we just published a paper on how we are making the extraction of chitosan and how it is.
Those are food safety verified, FSSI, like Indian system, we have the standard food safety, FSSI.
You can put it in any place, it's going to take 3
We are
years.
keeping on the fruits and all eatable items.
No, we are not selling anything. Currently, it's under, you are right. But chemically, it is chitosan. What we have done is we have used deep eutectic solvents, and then we are reusing the solvent for at least 5 times.
Because when we have the organic fruits, those either comes from Thailand or Washington apple, like from USA, we observe some very fine thin coating on the fruit.
That is carnauba wax.
Some wax. Is it a good?
Carnauba wax is considered to be safe because it has a FDA approval. Huh? I wrote a whole damn book on food coating. You can read that. Okay? On modern food coating. But anyway, it's not my primary interest because I'm not a chemist. So I have a colleague, Dr. Fay, who is taking care of it.
So in your presentation today, your main tagline was food, energy and water.
Yes.
So how you give the message, means how the foods, it means suppose
The message I wanted to convey here is that food has got no relevance for energy or petroleum. But remember, chitosan is also used as a flocculant.
Yes.
It's a green flocculant.
Yes.
So that was not to show you guys any applications per se. For me, it was to show you all how you can design your future research, think about an application, and then bring up your basic science. That was it, nothing else. Okay? I don't think you should follow any of the things that I'm presenting.
So in general, the renewable resource we have, even energy and water and carbon dioxide, so we can generate food, right? Energy again,
Yes, in relevance you can. For example,
for example.
I can grow rice in Sweden. Or I can buy rice at 1,000 times lower cost from India. So I will not be that stupid to spend 1,000 times more money. So if you have this carbon, hydrogen, oxygen and nitrogen and you want to make food, unless you provide me with the same price as I would buy 1 kilo of tomato in the village here, your research is worthless.
Plants making naturally, of course.
Yes, and that's the cheapest. So, you have to think about it, that how do you come up with something that is useful. So one of the first lesson I give my students is that don't make a Volkswagen at the price of a Rolls Royce. Okay? I hope I've given you the message. Thank you so much.